Hi and welcome everybody to my talk about ambiguous file system partitions. My name is Janine Schneider and I'm a PhD student at the IT Security Infrastructures Lab at the Friedrich-Alexander-Universität Erlangen-Nürnberg. And I conducted this research together with Maximilian, Eichhorn and Felix Freiling. And yeah, let's dive into it. As you may already know, forensic tools rely on the correctness and existence of data structures. And for example, if you want to analyze a file system, then your forensic tool probably relies on the correctness of the file allocation table or the data in an MFT entry. And therefore, many forensic tools assume that these basic data structures are trustworthy because they usually are and they have to. But this must not necessarily be the case. And we were wondering what happens if this is actually not the case. So what we did is we created ambiguous file system partitions. And this means that we incorporated a fully functional file system within another file system such that both file systems can be used. And what we did is we created a partition in which two fully functional file systems coexist, and for which it is not totally clear which file system is being in use. And this poses a challenge to current forensic tools. And yeah, why did we do this? We did this because forensic tools are a critical point in any investigation, as Mundram et al. Said. And forensic software has to fulfill the highest quality criteria, both in qualitative and quantitative ways. And therefore, we think that advanced forensic tool testing is a very important topic, and that it is also important to find the limitations of current forensic tools and to see how they handle ambiguity. So what we did is we examined several different file systems regarding their potential for creating ambiguous file system partitions. And we developed a taxonomy of ambiguous file system partitions, which can be used to classify different combination approaches and evaluate their quality in regards to the possibility to use them for forensic tool testing. And we created 3 fully functional ambiguous file system partitions. I will not describe all 3 of them, but let's see how the time, what the time will allow. But yeah, we created 3. And yeah, we showed that apparently simple forensic analysis of file systems or basic data structures can be non-trivial, and that forensic tools are not really well prepared for ambiguous file system partitions. So let's have a look at the taxonomy I talked about in the introduction. And the taxonomy has 3 dimensions or properties, if you like this term better, and they are all describing how ambiguous file system partitions are created and how the data structures are located, how they are placed, how good the usability is, and yeah. So the first dimension is placement, and placement refers to the location of data structures or the file system in the file system. And we defined 3 cases of placement. For simplicity, let's assume we have file system X and a file system Y, and they are overlapping if they partially superimpose each other. For example, the first sector of X may be located at the beginning of the partition, and the first sector of Y has an offset to the beginning of the partition, and thus they are overlapped. And we have a subset if, or y is a subset of x if y is completely embedded into x. And the third case is identical placement, and file system x and y are identical with the respect of placement if both file systems are completely superimposed. And in this case, the data structures of the two file systems must be integrated into each other. So this is the most complex case for placement we have. The second dimension of the taxonomy is stability. Stability refers to the overwriting of data. So we say that a file system X respects another file system Y if the usage of X does not interfere with the current or future usage of Y. And if X does not respect Y, then the usage of X eventually makes it impossible to use Y or overrides data of Y. And as before, we have three cases: the mutual disrespect, where file system X does not respect Y and file system Y does not respect X, so they both override each other. We have the directed respect, where file system X respects Y, but Y does not respect X. And the mutual respect, this is what we want to achieve when we create such partitions. In this case, file system X respects Y and Y respects X. We have the third dimension, which is accessibility. And accessibility is the ability to use the file system in a default way without needing special parameters to find the beginning of the file system in the partition. And this is actually what we see under A here. It's an unmodified accessibility. And B, the modified accessibility, means that the user have to have some knowledge about the ambiguous file systems. Okay, let's have a look at an ambiguous file system example. And the main idea while we created this file systems was that we have one file system which serves as a host and then place another file system into this host file system as a guest. And the guest is placed into unused areas or allocated areas with non-essential data. And let's have a look at a more or less simple case. I skipped over the file system background because I at least hope that you have some knowledge about Ext3 and FAT32. But yeah, it's not this complex. So let's just have a look at it. So as you may already noticed in this picture, the FAT32 data structures are depicted in blue and the Ext3 data structures are depicted in red. And so the first thing what I want to mention is that the X superblock has a fixed offset of 1024 bytes. And the FAT boot sector has to be located at the beginning of the partition. So these two file systems build a perfect match. So we can just easily write the boot sector of FAT into the unused offset area of Ext3. Then we just regularly place the Ext3 data structures after the boot sector, and after the Ext3 data structures, the FAT32 data structures are placed. And one important thing here is that we have to set the sector size to 2048 bytes. I will come to that in a second. And it's also important that we don't have a backup FAT boot sector. And yeah, as you can see, maybe here, I don't know if you see my mouse, I hope so. And the reserved area spans, the FAT32 reserved area spans over the whole data structures of Ext3. And therefore we have to adjust the reserved area size. And this is where the 2048 sector size plays a role, because If we set the sector size smaller, then this number will be too big to fit in the FAT data structures. So this is important to adjust the reserved area of the FAT file system. And after we did this, all needed data structures are placed and here. And as I said, we don't want the file systems to override each other. So next step is to mark blocks used by the FAT file system as allocated in the group descriptor table and the block bitmap of the Ext3 file system. We also have to reduce the number of free blocks in the superblock and the backup superblock. And of course, we have also to mark the blocks used by Ext3 as bad in the file allocation table. And that's it. We're actually done. We have created an ambiguous file system partition example. And what we want to do next is, of course, we want to use it. And therefore, we have to protect user data from being overwritten. And there are two ways to achieve this. We can either protect user data by dividing the whole storage between Ext and FAT, or we can assign blocks flexibly. So if we decide to divide the storage, then this is of course more convenient, but it's conspicuous because the number of damaged blocks are rather high. So the flexible assignment is more complex, but less conspicuous. And this is why we chose to do this for our ambiguous file system partition examples. But if you want to divide the storage, you could, of course, do something like even blocks belong to Ext and odd blocks belong to FAT, and then just mark the corresponding blocks in the data structures of the other file system. Okay, another example, a more complex example would be this one. Here we have three file systems over each other. So the Btrfs file system is the host, and the HFS plus file system is the guest in Btrfs. And then we have a FAT32, which is a guest in the HFS plus file system. And I will just go quickly over this example because it's very complicated, but let me say this much. HFS plus also has a fixed offset to the volume header, which is a similar data structure to the superblock. And as before, FAT32, the boot sector, nicely fits into this unused offset data space. And Btrfs is quite flexible with the location of the data structures. So these three file systems are very well, they can be used very good for creating ambiguous file system partitions. The interesting part is the prevention of data, the prevention of overwriting data. So HFS plus and FAT32, it's pretty easy to protect data being overwritten in these two file systems, but Btrfs has many complex structures, and therefore it is non-trivial to manually adjust these structures. So currently this example has overlapping placement and in some cases respect, but so HFS plus and FAT32 respect one another, and they also respect Btrfs, but Btrfs currently does not respect HFS plus and FAT32. Okay. So, of course, we also did an evaluation. First, we did a functional test. What we did here is we mounted each file system individually, created several files, marked the corresponding blocks as damaged, and unmounted the file system again. And afterwards, we mounted each file system again and verified that the files were indeed accessible and readable. And we also checked whether file system data was ever overwritten, and this was not the case in any of our tests. And we therefore concluded that as long as the concrete file system type is known, the file system can be used in a standard fashion without interference with the other overlaying file system. And the file system has to be known because if you mount the file system, you have to tell the operating system which file system you want to mount, but you don't have to know any offset values or stuff like this. So after we evaluated the function of each file system, ambiguous file system partition we created, we also did a tool test because, as I said in the beginning of this talk, we wanted to see how forensic tools handle this ambiguity. And therefore, we conducted some test analysis with some forensic tools. We used 5 common forensic tools, namely test disk, the sleuth kit, autopsy, X-rays, and magnet forensics. And this is a summary of our tests and the result of these tests. Oh, I see here's something missing. This should be HFS plus and FAT32, and this case is Btrfs, FHS plus and FAT32. But the other combinations do look all right. Okay, so let's discuss the results. So what we did with test disk was we tried to analyze Ext3 and FAT32, and test disk was able to identify and analyze Ext3, but FAT32 was not recognized. There is a function which is called deeper analysis, which we use to further test the tool. And while we did this, there was an indication showing up that the FAT file allocation table exists. However, this message was no longer displayed after the completion of the analysis, so it just popped up and then was gone. And the tool also indicated that there are partitions with overlapping fragments, but when looking at these fragments, an error message was displayed and the fragments were described as damaged. So we have at least an indication that something could be odd here. And for the combination of FHS plus and FAT32 and Btrfs, HFS plus and FAT32, only the guest could be recognized, but also HFS plus could not further analyze because TestDig has currently no HFS plus support. Also, there's no Btrfs support, but yeah. So for the sleuth kit showed a message cannot determine file system type, but the sleuth kit at least gives you a hint which file system it could be. So, and afterwards the user have to decide which file system shall be analyzed. And yeah, the current version of the sleuth kit does not support Btrfs. Or I know that there is a plugin for Btrfs, but the plain version does not. And but if the correct file system, so Ext or FAT or HFS plus is used as a parameter, then all files can be viewed and everything works fine. Autopsy produces similar results, but yeah, this is not surprising because autopsy is based on the sleuth kit, so same results here. And for X-rays, X3 was not able to recognize any of the embedded file systems, so the guest file systems could not be analyzed. It is also not possible to analyze Btrfs, and yeah, but the Ext3 and HFS plus files can be viewed with X-rays. And for Magnet Axiom was also not able to recognize the embedded file systems and Btrfs, but Ext3 and HFS plus files could be viewed. So what naturally arises is the question, how can these ambiguous file system partitions can be recognized? And what I did not say is that some of these tools we used have some file carving functionality. And of course, with file carving, you can find all of the created test files, but this is just because file carving does not rely on any file system structure. But it tells us again that file carving in many cases can give us at least indications what's on a file, on a partition, and should therefore be some kind of standard procedure if the storage isn't too big. But ambiguous file system partitions can also be recognized if the investigator or the forensic specialist checks the data structures for irregularities, and irregularities in this case means deviations from what can be considered ordinary. Like, for example, I told you that we have to adapt the reserved area, and the reserved area got really big. So this could be considered non or ordinary. One can also check the position and size of certain data structures, the number of damaged sectors. If there are a lot of damaged sectors, then this could be a hint for an ambiguous file system. One can also check or look for unusual file system labels like Btrfs labels. If you have a FAT32 file system and you see a Btrfs label, then something could be odd here. One could also check empty spaces or the size of allocated areas. These bullet points could all be hints for something ambiguous, ambiguous file system. So to conclude and to give you some ideas for future work, forensic tools should not be based on assumptions. This is what we can learn from these ambiguous file systems, and these ambiguous file system partitions also remind us that there is no such thing as a clear or trivial interpretation of data. So what would be cool is when, so forensic tools at some point they have to rely on the assumption that something is trustworthy, or they can rely on some data. But it would be great if tools could clearly communicate limitations, or if some ambiguities are detected, so that the investigator knows, okay, I have to manually check this. And for future work, one could create other file system combinations. There's also one could also create more difficult combinations in the sense of our taxonomy. So, for example, the identical placement could not achieved yet. It would also be great to have a tool which automatically creates ambiguous file system partition examples for further tool testing. And for the more convenient usage of these ambiguous file system partitions, one could create an automated storage assignment to allow a more seamless use of these partitions. And yeah, that's it. Thank you very much for listening. And yeah, it was a pleasure to present these ambiguous file system partition. Thank you so much.